Lesson 1.5, modeling exponential growth and decay. So these are the problem-solving parts of exponential functions. So let's take a look at what types we have. So there's 5 different kinds of problem situations that we have that will be modeled by exponential equations. The first kind, we talk about population growth. We also talk about bacteria growth. We also talk about half-life and radioactive decay. We also talk about financial growth. And we also talk about depreciation. Okay, so let's take a look at what those mean. So here we've got tables of data. Again, with tables of data, we need to be able to fill out the rest of the table of data. We're given an equation here, and it wants us to fill in the table of values. Well, to fill in the table of values, we're going to substitute the x numbers where x is in the equation on the right-hand side, and then we are going to solve the equation for y. I'll give you a couple minutes to do that on both of those charts. When you are ready, push play when you're ready. Now you've had a couple minutes to do that. Let's take it up together. You've noticed that there is brackets around the exponent now. How come? We're using brackets because we have a fraction as an exponent. Okay, so that's why we're using brackets. So for you to do those equations, you would have had to use brackets like we discussed. So the answers we're going to get: 5, 10, 20, 40, 80, and 160. You're going to notice you get the exact same values on the right-hand side. 5, 10, 20, 40, 80, and 160. All right, what do we notice about our graphs? Well, they intersect at 0, 5, the y-intercepts. So they're going to intersect the y-intercepts. Then what else do we notice? We noticed that one of them was steeper than the other. So if we took a look at the graphs, one of them came up, and the other one came up much steeper. And again, it crossed the exact same y-intercept. That's what they intersected. All right, let's take a look at the next few examples. This is a population growth example. So again, we're given a table of values. When we're given a table of values again, we need to plug it into our calculator, into our lists, and do a regression. Make sure you read the questions correctly, because sometimes you can mess up which regression you're doing. This time they're asking us to do an exponential regression. So I'll give you a couple minutes, load those into your lists, and find the equation. Round each parameter to 2 or 3 decimal, well, let's go to 3 decimal places. We might need 4 for some of them, so 3 or 4 decimal places. Okay, we've got a couple minutes to do that. We're going to get an equation that looks like this. Y equals 0.0008, and our B number we got was 1.007, and it was run on, okay? So was the other one. The A and B values were both run on decimals. Now, exponent x, what you're going to notice is actually your calculator would have given you for A, you would have seen this value. It would have said 8.4525 E -4. Well, what does that E -4 part mean? Well, that's telling us that our calculators put that number into scientific notation for us. So it doesn't show us the zeros up front. So all we've got to do, the left mean, or the negative sign means we're going to move the decimal place to the left 4 times. So I move my decimal place to the left 4 times, and I get the answer that I created here, 0.0008. Okay, the exact same thing you're going to get with the B value. The B value would have given you a long decimal. We're just going to round to 3 or 4 decimal places. All right, letter B is saying, assume the same growth rate is going to happen. So we want to estimate the population in the year 2020. So the way we solve this is we're taking a look at it. We need to know, what are we given and what are we solving for? Are we given an X value and solving for Y, or are we given a Y value and solving for X? So that means we have to take a look at our table of values. Year is our X value because it's list 1. Population is our Y value because it's list 2. So let's take a look at this. If we have a year given, that means I have an X value. Whenever we have an X value, we can solve it algebraically, where we can put the exponent in, or we can do a second trace feature on the calculator. So since you already have the equation in your calculator, it's easy to use our second trace features. So you're going to do second trace number 1 value. Now when you hit second trace number 1, what's going to come up is x equals. Well, we know what the x equals number is. It's 2020. So you're going to type in 2020 and then enter. That's going to give you the intersection at 2020. What is the graph at 2020? It will give you the y value. So now when you type that in, the y value it's going to give you is 1350. That's all we got. But we have to remember that all of those numbers in that bottom row there for the population, those are per 1,000. So we have to times each one of those numbers by 1,000. So the number we actually got, we need to times by 1,000 to find the actual population. So the actual population in letter B, so the answer for B, the actual population is going to be 1,350,000 people. Okay? So all we're doing is we are rounding that, but we're timesing by 1,000 so we can have our value in thousands. So we have a correct value for our population. Now letter C is saying, well, we want to know the growth rate at an estimate when the population will reach this many, 1.5 million. Well, we know that in our row, the population row, it's per 1,000. So that means in order for me to put this into Y2, because it's a Y number, I'm going to put it into Y2. I can't put in 1,500,000. I need to divide that by 1,000 so that it matches the information I'm given in my table and what the graph is showing me. So that means you just basically take off the 3 zeros. So in Y2, you're going to put in 1,500. So 1,500 is what you're actually going to put into Y2. All right, do the Y2, do an intersect, and the value you're going to get is around 2034.95 and so on. It runs on forever. So that means around the year 2035. So around the year 2035, the population will reach 1.5 million. Okay, let's take another example. This situation, we're talking about bacteria growth. Typically, bacteria growth, they give us the equation, but sometimes they don't. If they don't, they usually talk in terms of percentages or of what our starting amount is. So what we like to do is we basically like to read through the question first, and then we try to label our equation the way we know it's labeled. We usually have our equation look like this: a times b exponent x. But now our x is going to be x over t, okay? Or t over p, whichever you like to do. So right now, we've got y equals 700 times 5 exponent t over 6. Now it's telling us that the pt, the y here that I have, those are identical, that's what it means. They're telling us the number of bacteria, so the total population of bacteria. The 700 is standing for the starting amount of bacteria we have. What is the 5 telling us? Well, it's telling us that it's multiplying by 5 every time. Well, what's that 6 telling us? It's telling us that it's going to multiply by 5 every 6 hours. Because 6 is the period of change, so it's going to be our multiplication factor. So how often does it multiply by 5? Every 6 hours. Okay, so if we take a look at it, it's asking us, for letter A here, determine the value of t. So I'm solving for x, and I'm given a y number. Remember, when we're given a y number, we put our equation into y1, and we put the other y number into y2, and we do an intersect. Now, this is going to create a problem where we might have to take a look at our, what am I trying to say? At your boundaries, meaning your window. If your window is out, you're going to have to extend your window. So 87,500 is my intersection that I need to find out. That means that I'm going to have to take my graph to at least 90,000 so I can see the 87,500. But this question actually wants us to solve it algebraically using same base. So let's do that together. So we're going to put 87,500 equals my equation 700 times 5 exponent t over 6. All right. First thing we do we get rid of the 700. Why can we get rid of the 700? Because the number on the left does not have an exponent attached to it, and neither does the 700. So we can divide them out. So the answer we're going to get there is actually going to give us 5. So we get 5 equals 5 exponent t over 6. So now I can drop the bases. I've got the same base. So what do we know about our bases? Well, first of all, oh, sorry, it's not going to give us 5. It's going to give us 125. Pardon me. Our bases are not the same. So 125 can be put into a base 5, though. We know that 125 is equal to 5 cubed equals 5 exponent t over 6. If you want to change t to x, that's fine. Now, since we have the same basis now I can drop my bases and solve for t. So I get 3 equals t divided by 6. How do you get the 6 off the bottom? Opposite process. The fraction line means divide, so I'm going to times both sides by 6 to get rid of the 6 on the right-hand side. So we're going to get our final answer of t equals 18. Now let's take a look at what that means in terms of the question. So t equals 18, that means it's asking us when, okay? And we know that t is the time in years. So we know that in 18 years, the population will be 87,500. Okay, that's how long it's going to take us, or 18 hours, not years, pardon me. It's going to take 18 hours for the population to reach 87,500. Okay, let's take a look at the next example. Example 3 is about a half-life. We're talking about a half-life, so that means our B value is 1/2. So this question's talking about when you dive underwater, the amount of light that you have decreases the lower you go in the water. So on this particular information, it tells us that on a sunny day off the coast of Vancouver Island, a diving team recorded 100% visibility at the surface. So at the top of the water, you can see 100%. However, but you only have 25% visibility when you're 10 meters below. Now, the team determined that the visibility of the dive could be modeled by the equation they're showing us here. Now, what does AX and AO stand for? Well, AX, it tells us over here on the left-hand side what all of these stand for. They're telling us AO represents the percent of light at the surface. So we know at the surface we have 100% light. Then it's telling us that X represents the depth in meters, and H represents the depth in meters where it's half your original visibility. Okay, so the H stands for half. Okay, half the original visibility. Then they're telling us that on the left-hand side, the AX is representing the percent of light at the depth of X meters. So whatever meters you have of X, the AX tells us how deep you are, okay, or how much percentage you can see at that depth of X. So 25% visibility, we need to solve that equation. We're going to do that together first. And then it asks us another question. It says, what will the depth be at half the visibility of the surface? Okay, well, half the visibility, if we have a 25% visibility at 10 meters, that means it's 100% has reduced. If I take 100% and I cut it in half, I get 50%. I cut that in half again, I get 25%. I cut that in half again, I get 12.5%. Well, I know that at 25%, I'm 10 meters below the surface. So that means it's gone through halving it twice. So something was halved twice. All right, so let's take a look at what that's going to mean for us. So we're going to solve it first using the 25% visibility and our 10, because we know those digits. So let's solve those together. So we put 25 on the left-hand side for our AO, or our AX, pardon me. Our AO is 100% visibility. Half-life, exponent, X, or pardon me, we don't know the H, but we know we're 10 meters below the surface when we can see 25 meters, or when we can see 25%. We know that we're 10 meters below. That's what that 10 stands for. Okay, we can solve it algebraically, or you can go in and you can solve it with y1 and y2. If we solve it algebraically, we're going to divide both sides by 100. We're going to get 1/4 equals 1/2 exponent 10 over h. Now, what do you notice about 1/4 and 1/2? They can be changed to base 2. Okay? So, currently I've got 1/4 would be 1 over 2 squared. 1 over 2 is equal to 1 over 2 exponent 1 exponent 10 over h. Now, when I want my 2's to come up, right now I've got bases of 1/2, but it's not exactly 1/2 because my bottom number is squared on the left. So that means I've got to take my digits and put them upstairs. So I'm going to have 2 to the negative 2. All it does when we flip it is it changes our exponent from a positive to a negative. And then this guy will be 2 to the negative 1 times by the exponent it already has, 10 over h. So now our left-hand side, 2 to the negative 2. Our right-hand side, we're going to multiply that exponent. We're going to get 2 to the negative 10 over h. Okay? Now, we can drop our bases because we all have the same basis of base 2. So I get negative 2 is equal to negative 10 over h. Now I'm back to solving normal equations. How do you get the h off the bottom? You multiply it to both sides. So I get negative 2h equals negative 10. We're going to divide by what's in front of the variable. So we're dividing by negative 2 to both sides. We're going to get h equals positive 5. So that means that our h, our half-life, happens every 5 meters. That's what that h is telling us, that every 5 meters, the visibility cuts in half. Let's go back to our example at the top and see if that works out. So, if I find out that it's 5, so if I take 100 and I'm cutting it in half to 50%, that's going to be at 5 meters. Okay, at 5 meters it's half. Another 5 meters, it's going to be 10. If I go to 12.5, it's going to be another 5 meters. It's going to be 15 meters. Okay? So at 15 meters below, you'll have 12.5% visibility. So every 5 meters you go underneath the water, your visibility is reducing by 5. That's what that h is telling us. So when is it at half its visibility? Well, half of its visibility, we're going to find the x. We don't know. We're going to pretend we don't know x, but we do know h now. We found h is going to be 5. So now let's calculate what it would be for solving this question when it's half the visibility. Okay, let's take a look at that. Okay, so what we're doing is we're proving that the x is 5. So, or sorry, yes, x will be 5. So we're going to have 50% visibility equals 100% visibility. Half-life of, we don't know x, we're solving it, but we know every 5 meters it cuts in half. So now we solve it normally. We can solve it by dividing both sides by 100. That's going to reduce to 1/2 equals 1/2 exponent x over 5. Well, right now I've got both of the same base. My bases are both 1/2. Well, what is the hiding exponent on the 1/2 on the left? It's hiding 1. So now I can drop both my bases. I've got a 1 equals x over 5. Again, how do we get our 5 off the bottom? We multiply it to both sides. 5 times 1 is 5. So we get x is equal to 5. So it does confirm that every 5 meters, it reduces by half the visibility. Okay, example 3 is talking about radioactive decay. Now, some of this you're going to need to put into a window. So your window, a good window to use for this question is going to be negative 10, 50, count by tens, negative 10, 200, and count by tens. That should be a good window for these questions. So let's take a look. It's got cesium-137. Now, a lot of kids are misinformed and they assume that 137 is the amount of cesium that you have. 137 is not the amount. It's part of the name. Cesium-137 is the name of that element. It's a radioactive element. So it's saying that the percent of a cesium element left can be modeled by this half-life. So here it's talking about the initial amount is going to be 100% of the cesium. T is time in years. So I know that AO, my initial amount, is 100. So my equation is going to look like this. Y equals, or AT equals, 100% times a half exponent T, or X, over 30. Okay? Question A is saying the sample will decay to half of its original amount in how many years? Okay, well, if we want to go half of our amount, what is half of 100%? It's 50%. So that means on the left-hand side of the equation now, I'm going to have 50% instead of my Y. So again, I'm going to solve the equation either algebraically, or I can solve it in my calculator using the window that I showed you. Let's do it algebraically. So I'm going to have 50 equals 100 to the half-life of exponent T over, 30. T over 30. Okay, if we divide by 100 on both sides, I end up with 1/2 equaling 1/2 exponent T over 30. And yes, your fractions should be in brackets. Now I've got the same base again, 1/2 and 1/2. I can drop my bases, but what's the hiding exponent on the base on the left? Don't forget, it's a hiding 1. So I can drop my bases now, and I've got 1 equals T over 30. Again, our last step when we've got something on the bottom is to multiply it out. So I'm going to multiply out 30 to both sides. So I'm going to get T equals 30. So that means it will be half of its original amount in 30 years. Now, what do you notice about the bottom number? That's how often the half-life happens. So the 100 is going to cut in half in 30 years. So is it surprising that when we put 50 on the left, the half amount, we got an answer of 30? No, it's not surprising. Now, if I change that 50 to a different number, if I change it to any other number, that number 30 is going to change. It won't be 30 any longer. It just so happens that it's going to be 30 because 50% is half of 100%. And the bottom number is telling us that every 30 years, it's going to cut in half. All right, letter B is saying, well, how much do you have left after 10 years? Well, we know that X is time, or T is time. So you've got an X number or a T number there. So that means you can actually substitute it in where T is. So you can put in 10 over 30 as your exponent. And if you do that, you're just going to solve it. And it says round to 1 decimal place. So you're going to type in your calculator 100 times 1/2 exponent 10 over 30. Yes, the brackets are necessary because there's fractions. The 1/2 has to be in brackets, and so does the other exponent, 10 over 30. Okay, type that in, push pause now, push play when you're ready to continue. Okay, hopefully you've noticed that your answer you're going to get is going to be 79.4. So after 10 years, 79.4% is still left over. All right, letter C says, when will it decay? So when? How long will it take to decay to 10% of its original amount? Well, now I'm given a Y number. Percentages are Y numbers. So when I'm given a Y number, there's a couple different ways to do this. I can put 10% on the left-hand side of my equation, 100 on the right, 1/2 exponent X, or time, over 30. It can be X over 30 or T over 30, whichever you prefer. We can do it this way and solve it algebraically, or I can put my equation into Y1, my 10 into Y2, and do an intersect. And sometimes that's easier. When you do that, you're going to find that you get 99.7. It's going to take almost 100 years for that element to reduce down to be 10% of the starting amount. Okay, let's take a look at the next type of examples. The next type of example, we're talking about financial growth and borrowing money. Okay, whenever you're borrowing money, we've changed the equation now. The Y equals A times B exponent X now changes. It's no longer Y equals. The Y changes to the letter A. A meaning total final amount. The A value changes to the letter P. P stands for the principal amount, meaning what you start with. Okay, the amount you start with. And then the B value, it's your interest. Now your interest is going to be I, but it's 1 plus I. But the one thing you have to remember is that I must be in decimal form. So when we're given an interest as a percent, we need to divide it by 100 to get it out of percent form and put it into a decimal. And it needs to be a decimal to be put into the equation. And all they've done is they've changed X now to N. And N is talking about the number of compounding periods per year. Okay, so how many times does it compound the interest? Meaning, how many times do you earn interest? Okay? All right, so the minute you see compounding, you know there's a plus sign. Borrowing money, plus sign, money you owe, or money that you borrow if you're having a loan, or if you're growing money as interest in a savings account, you're always going to have a plus sign. How come? Because it's gaining interest. So it's always a plus sign, even if you're borrowing money. A variation of the example would be to change the plus sign to a subtraction sign. And that's coming up in the next example when we deal with depreciation. This is all talking about growth. So again, it's an exponential equation. So what are we going to notice? It's going to grow and go up. Okay? The y-intercept is always our A value, which is now our P value, which is our starting amount. All right, let's look at a couple examples and see how this works. The one thing we have to remember is whenever we have a compounding period, whatever we do to I, we must do the opposite to N. So if our compounding says annually, we times by 1, divide by 1, we really don't have to do anything to I and N. But the minute it changes our compounding period to monthly, quarterly, it could do yearly, any of those compounding periods, that means we have to divide the I by that number, by the number of compounding periods. And whenever we've done to I, we do the opposite to N. So we're going to have to times N by those compounding periods. Let's take a look at the first example. So Yvonne has a balance of $3,215 in her savings account. The account pays 2.4% interest every year, and it's compounded annually. Annually just means one time a year, so N we multiply by 1, I we divide by 1. We really don't have to do anything to N and I. All we've got to do to the interest is divide by 100 so we can put it in the equation. Okay, let's write the equation then. A stands for final amount. How much do I have in the end? Our principal amount is what we start with. So Yvonne's starting with $3,215 in our account. I'm going to have 1 plus, you changed your 2.4% to a decimal, 0.024, now exponent x or n. Doesn't matter if you use n or x. Now the question's asking us, how long is it going to take the balance in her account to reach $5,000? So again, we've got to realize, am I solving for an x number or a y number? Well, I need to solve an x number because it's asking me time, how long. So I'm solving for x. When you solve for x, that means you're given a y number. So when you're given a y number, you're going to put that guy into y2, put your equation into y1, and do an intersect. That's the easiest way to do these types of questions. Now, do you have to do it that way? No, you could have done it algebraically as well. A good window for this equation would be 0, 30, 1, -10, 9,000, and count by 1,000. That's a good window to use for this question. So if we're doing it graphically, y1, y2, we will do an intersect. We're going to notice that it comes up with an answer for x. X is going to be equal to 18.6 years. And if it wants us to round to the exact number of years, we'd round to 19 years. So we would say around 19 years. So it's going to take her 19 years to gain up to 5,000 in her account. Now, remember, that's not the amount of interest she's earning. That's how much she has in her bank account at the very end of those 19 years. Okay, let's take a look at B. B says an investment of $500 earns interest now 6%, but we're compounding semi-annually. Semi-annually means 2 times per year. So that means what I have to do to I, I'm going to divide I by 2. And my n, I would have to times n by 2. Now, I'm going to be solving for n, okay, because it's saying how many years. So I'm going to solve for n or x, and I'm going to be given a y value, meaning a money amount. So the question's saying in B, how many years or how long does it take for you to double your investment? Well, we need to write our equation first. So A wants our equation. So writing our equation. We don't know what we're going to end up with, but we're starting with $500. 1 plus our interest. We take 6 divided by 2 gives us 3%. But we need to divide that 3% by 100, okay, to get it into decimal form. So it's going to become 0.03 exponent n or x, whichever you like. Okay, so that's our generic equation we would be given. Now, on B, again, it's asking us how many years would it take the final value. A, we want to reach double value. Well, we're going to double 500. Okay, it's always, if it says double your initial value, that's doubling what you start with. So that means I want to reach $1,000 in my account. How long is that going to take, is what they're asking us. Okay, so I'd have 5,000 equaling 1,000 equaling 500 times 1.03 exponent n. All I've done is I've added those numbers. Do you have to? No, but it doesn't matter if you do. No, it doesn't. Now again, you can put the right-hand side into y1, the left-hand side into y2. Does it matter? No, you put the left into y1, you can put the right into y2. It doesn't matter. You can still get the same intercept. And then we do an intersect on it. Okay? We're going to go second, trace, intersect. Take a couple minutes to do that. Push pause now and play when you're ready. Okay, you've got a couple minutes to look at that. You're going to find out that your x value or n value, you're going to find out it becomes 23.449, and it runs on forever, of course. So we're going to say around 23 to 24 years. Okay, it takes 23 or 24 years at that interest rate to double her money in her account. Now that means she's not putting any other money in the account. She's just letting that $500 sit there for 23 to 24 years. Okay, she's not touching it or taking money out or adding money to it. She just lets it sit there. That's how long it's going to take. If she just lets it sit there and doesn't touch it, it takes 23 to 24 years for it to reach double its original value. Okay, let's look at the question on the bottom for borrowing money. When we borrow money, interest is charged for the use of your money that you're borrowing during a fixed period of time. Now, if you pay your loan off in one payment at the end of the loan, you can use this compound interest formula. But if you're making regular payments all the time, you're not going to use this formula. The questions we only deal with are when we pay it off at the very end. So, let's take a look. Travis borrows $2,000 from his parents and agrees to pay off the loan in one payment after he graduates. Interest is charged at 3.5% per year, compounded annually. So, do I have to do anything to N and I? No, because it says annually. Okay? But his parents are charging him interest. All right. Let's write our equation. So our equation is going to look like this. A equals our initial amount of $2,000 he's borrowing, our interest, 1 plus I. Now, I we have to divide by 100 to get it out of its percentage. So 1 plus 0.035 exponent n. N or x, again, doesn't matter. So now what we're going to do, we're going to solve the equation. It says, how much do you owe at the end of the second year? Well, second year, you know x. Okay, you know your n. So now you're going to substitute. I wrote that wrong, didn't I? Okay, let's try that again. Substitute. Okay, you're going to substitute 2 for n in the equation. And that's how you're going to solve that one. How come? Because you're asking for how much. That's a y value. That's a number value, an amount of money. So you're going to be asking to solve for y, or the a value here they call it. Okay? So all you've got to do, put in 2 for n, type in your calculator, and see what you get. Okay, when you did that, you're going to get exactly $2,142.45. So that's how much he has to pay his parents back. So how much interest does he actually pay? Well, that's what B's asking us. If he pays it off in 2 years, how much interest does he pay? Well, the 2142 is the total amount he has to pay back. That's not the amount of interest. How do you find the amount of interest? You're going to take the A value and subtract the P value. So you're going to take the amount that you accumulated to, and you're going to subtract what you started with. So we're going to take 2142 and 45 cents, and we're going to subtract our starting amount of $2,000. And what do we know? The interest amount is $142.45. That's how much he paid in interest. Now, the letter C says he isn't able to pay it off in 2 years. And when he eventually pays it off, he pays $458 in interest. So in order for me to find out how much he had to repay, I need to take $458 and add it to my original $2,000. That's going to give me my A value. And then I'm going to be solving for N. I need to solve for the time period. Okay? So, we need to write the equation on the first part here. So we're going to have 2458. Now, why is it 2,458? Because 458 is only the interest. You must add it to the original amount to get the total amount you have to pay back. Equals our original 2,000, 1.035, exponent n or x. Okay, so there's our equation. Now, letter 2 says solve it algebraically and determine the time period for the loan. Okay, let's solve this algebraically. When we solve it algebraically, we're going to divide both sides by 2,000. On the left-hand side, that's going to give me 1.229 equals 1.035 exponent n. Now, how do I get rid of that n? I notice my bases are not the same. Our decimal numbers are different here. So we can't just drop our bases and solve for n. We need to use logs. That's why we've learned logs. So we are going to solve this with logs. So what do we do again? We write the word log in front of both sides. So I'm going to have log 1.229 equals log 1.035 exponent n. Now we know with our log laws to get that n out of the exponent, the n is going to tuck out in front of the word log on the right hand side. That's how I bring it down out of the exponent. So I'm going to have log 1.229 equals n log 1.035. Now remember, the n is sitting beside it in front. If it's beside it, means multiply. So how do I solve for n? Well, I got to divide out what's sitting beside it. So I'm going to divide both sides by the 1.035. Well, what did you notice? I just put the 1.035. Thank you for catching that. We cannot just divide by the digit. The word log is there on purpose. You need to divide by log 1.035 on both sides. Okay, I'm going to give you a couple minutes to do that. Push pause now and play when you're ready. You're going to get an answer of n equals 5.99. So that's going to round to roughly 6 years. So that means he would have taken 6 years to pay off his loan to his parents. Okay, let's take a look at our last type of question. We're talking about depreciation. And that's when we are reducing money. So something is losing value. And what usually loses value? Vehicles do. All right. Okay, our last example here, we're talking about vehicle depreciation. So when we do vehicle depreciation, the only thing that changes in the interest equation is the plus sign changes to a subtract sign. Everything else stays the same. Only this time, they're not going to compound anything. You will never see the compounding word in a depreciation question. So you never have to worry about dividing or timesing I and n. All right, let's write the equation with what it's telling us. So we bought a vehicle worth $35,000. The depreciation rate of this type of vehicle is 14.3%. So again, we need to take our percentage and divide it by 100. So I'm going to get 0.143 as my as my I value. That's going to be my I in my equation. So let's write our equation for us. We're going to have A equals our initial value, what we bought the truck or car for, 35,000 times 1 subtract I. 1 subtract 0.143 exponent n. Okay, letter A is asking us now, how much is it depreciated? So it wants to know how much value it's lost after 3 years. Well, the A amount doesn't tell us how much it's lost when I figure this out. It's going to tell me what the vehicle is worth. Okay, it's going to tell me what the vehicle's worth. So how am I going to find out what the actual depreciation is? I'm going to have to take my 35,000 and subtract my A value. So you're taking P here and subtracting A in the end. Okay, it's opposite of what we did for our growth questions. There we took A subtract P. Here we're taking P subtract A. That's going to tell us how much our depreciation amount. So how much value did it lose? Okay? All right, I write very large, so this is not the answer for B, but I'm doing all my work right now under letter B for question A. So, how much the vehicle depreciated after 3 years? Well, 3 years is time. I'm going to substitute that in for N. Type that in your calculator and see what you figure out. Round it to the nearest dollar, or no, not dollar, penny. So you have 2 decimal places after the decimal. Okay, so your answer you're going to get for A, you're going to get its worth. So the A value gives us $22,029.80. That's how much it's worth. So now I need to find the depreciation. So depreciation is equal to A or P subtract A. So I'm going to say my depreciation amount, depreciation money amount is going to be $35,000. Subtract my $22,029.80. When I subtract that, my vehicle after 3 years has depreciated $18,970.20. Okay? So it's only worth $22,000 because it's depreciated almost $19,000. All right, letter B is saying, how long is it going to take the vehicle to be worth nothing? Now remember, we're dealing with an exponential equation. One of the properties of an exponential equation, will my graph ever touch my x-axis? Will it ever touch? No. It's going to come very, very close. But remember, with exponential equations, we do not have an x-intercept. So really, we're not going to be able to find when it hits 0. We're going to be able to find when it hits very close to 0. All right, so I want everybody to give that a try and see what you get for that. Okay? Push pause now and play when you're ready. Okay, when we solve it algebraically, we're going to find for letter B that we're going to get it close to 0. We're going to get 0.00148, and it runs on forever. So it's really close to $0. Okay, when is it really close to $0? After 110 years. So it takes 110 years before it drops to almost 0. Now, what is one of the properties we know of an exponential graph? Typically, and especially for depreciation of vehicles, the graph is going to reduce very quickly, and then it's going to kind of level off and reduce slowly in the end. So our initial drop is going to be fast, and then it's going to even out. Okay? So that's why it depreciates so much at the beginning, and then the depreciation levels off. It takes a long time for it to keep depreciating almost right to 0. All right. The one last question we're going to look at is the student practice question at the very top of that page. So we're just taking a look at the top one here about Freya. So Freya's got $3,400 in an investment that's earning 5% interest compounded annually. So again, we're looking for the word after compounded. That tells me what I have to do with I and N. And in this case, annually means I do nothing to I and N. So it wants us to find the number of years. So how long, so we're solving for N, will it take the balance to be over 5,000. Okay, well, we're going to use this equation, and we're going to write our equation in that format. So we're going to get A equals our starting amount, $3,400. Interest again up here, I got to divide by 100. So I'm going to have 1 plus 0.05. Now, why am I putting a plus sign, not a subtraction? Exactly. It is growing money. It's an investment. Okay, you're gaining interest. You're not losing money here. Okay, so we are solving for n. Okay, and why are we solving for n? Because the question said to us, it wants to know, when is she going to have more than $5,000 in her account? Well, first of all, we need to know when she's going to have exactly 5,000. So we're just going to substitute the A value as 500. So we could put this into our calculator. We could put in 5,000 into Y2. Into Y1, we put our other equation. Again, n you must change to x in the calculator. Put that into Y1, Y2, and do an intersect. Solve for x. Push pause now and play when you're ready. Okay, for those of you that got stuck again, we realized and we showed that we have a different window. We need to use the appropriate window. Now, sometimes if you hit zoom 0, it'll find you your window for you. We could have also solved it algebraically. Okay, so first of all, when we put that number in and we do our intersect, almost all of you should come up with 7.9. Now, what does that actually mean? Well, that means in 7.9 years, she will have exactly $5,000 in her account. So it wants to know, when will she have more? Surpass means more. When will she have more money in her account? Well, that means after 8 years. You have to round this up. So we're going to have 8 years there. So around 8 years, we'll take her to surpass or be more than $5,000 in her account. Okay, this concludes the lesson of 1.5, Exponential Growth and Decay. Stay tuned. I will continue right now, and I will give you the answers for the student practice section. Okay, the answer for number 1 here, you're going to find after 19 quarters, 4 years, 9 months. How come? Because you're going to take a look at this. It's A equals 7,001.019 exponent x. And in Y2, you're going to put $10,000. Okay? Where did this number come from? Well, again, you're compounding quarterly. So you had to take your 7.6 and divide it by 4, and then divide by 100. That's where that 0.19 comes in. Number 2, the answer for number 2, you're doubling your money. Okay? And you're compounding annually. Don't forget, you need to divide your interest by 100. You're going to get it happens after 21 years. On number 3, in order to graph this one, you need the window. 0, 3,000. Count by 50s. 0, 10,000. And you can count by thousands. Okay, that should work. Now, we looked at number 3. Number 3, you should get 1298, so 1,298 days, or anywhere between 3.6 to 3.9 years, anywhere in there. Depending on your rounding, that's going to give you a rough value. Now, it wants to know how much it's going to take to double it. Well, doubling your initial value, the double the value is $7,800. So that's what you would have put in Y2. Okay. Now, it wants daily. Okay. So daily, how would you solve your equation? You would have this. Your equation would look like this. A equals 3,900. 1 plus 0.195. And this part, not the 1, but only that part, you divide by 365. All exponent x or n. Now, when you do the dividing, what's that actually going to look like as a decimal? You're going to have 3,900 bracket 1.000534. exponent x. Okay? Doubling its value. And again, in the a value, you would have this in y1. y2, you would put 7,800. That's double the original value. Okay, let's take a look at the next couple questions. On number 1, a, you're going to have an equation of a equals 30 million times 2 exponent x. D, how much is it in 40 years? Well, when you actually type it in, you're going to get 3.2985 times 10 exponent 19. 80 years, 3.627 times 10 exponent 31. And 30 years, 3.22122. And remember, those are run on decimals. Okay, times 10 to the 16. I'm just showing about 3 or 4 decimals there. Now it says show that our growth rate is 1.75%. All we're doing is rewriting our equation. Instead of the 2, we're going to put 1.75. So we're going to say we've got 30 million. And again, it's a percentage. So we're going to have 1.0175 exponent x. How come? First of all, again, I'm going to divide that by 100, and then I'm going to take 1 plus that number. Okay. That's the equation. Letter D. Model the situation in terms of an annual growth rate. Okay. Well, how much is it going to be? That's your equation for the growth rate. Letter E. How long does it take to reach 40 million? Well, 40 million is going to go in your Y2. 30 million, the equation in letter C is going to go into Y1. You'll do an intersect, and you're going to get x is equal to around 16.58 years. So just over 16 and a half years, the population is going to reach 40 million at that rate. Well, let's take a look at the next example. Number 2. The equation you're going to come up with is y equals 59.366 times 0.981 exponent x. And this will go into y2 to do an intersect, and you're going to get 27.3391, etc. It runs on, so around 27 degrees Celsius. The window here, again, your window you should have used is -5, 50 and 1, -5, 50 and 1. That was a good window to use. Okay, number 3. Your equation is going to be a equals 100 times a half exponent x over 8.2. The window to use here, 0, 50, 1, -10, 50, and 1. B, how many days should it take for only 10% to be left over? Okay, well that's going to go into your y2. Do an intersect, you're going to get x equals 27.2391, etc. So around 27 days. Number 4. Number 4, we're going to write our equation. A equals 5,100,000 times 1.018 exponent x. Again, take your percentage and divide by 100. That's our generic equation. B, what should it be in 2010? So you substitute into x, 2010. And that's going to give us, now 2010, you actually don't put in 2010 for x because you're starting at the year 1998. So you're actually going to take 2010 and subtract 1998 to find the number of years. Well, that's about 12 years. So that means that you're substituting 12 in for x, or you can go second trace value of x is 12 if you've got the equation in your y1. Okay, when you do that, what would the actual population be? It's going to be around 6 million. So you're going to get 6,317,474.7 people. Now, can you have a 0.7 of a person? No. So typically the people, you never round up, you're just going to cut that decimal off. You're just going to Not even, it doesn't exist. Okay? Now, it asks us on B, when's the population going to reach 8 million? Again, we'll do an intersect here. That's going to go into Y2. You do an intersect, and you're going to get 25 years. Okay, well, you have to add 25 years to 1998. So 25 years after 1998, so 1998 plus 25 is going to give us around the year 2023 is when it's going to happen. Now, if you're struggling with this question, a good window to use would be 0, 40, and 1, negative 50, 10 million, and you're going to go up by 1 millions. That's your scale. That's a good window to use. Okay. Number 5, A equals 2500, 0.95 exponent x. How come? Decrease. So you're going to take 1, subtract I. Now don't forget, I you need to divide by 100. So it's going to be 1 minus 0.5, so you're going to get 0.95. Or 0.05 you're subtracting, pardon me. Okay. Now it says, what is the expected population for January of 2005? Okay. Well, for 2005, how many years is that after 2000? Well, that's 5 years later. So we're just going to sub into x, sub 5 for the x value. Okay, so put 5 where the x is and solve it. You should have got 1934. So that means the amount of fish, your population of fish, would be around 1,934. Okay? That's how much fish population. Now on B it asks how many years. You're solving for x or n here. How long is it going to decrease to half of the population? Well, your original population is 2,500. That means in Y2 you're going to put 1,250. That's your intersect. So you're going to put in 1,250 because that's half of 2,500 what you started with. Do an intersect, and you're going to get x equals 13.5 years. So it's going to take about 13.5 years for it to decrease to half the population. All right, number 6. Again, 18%. You are removing something. It removes pollutants, so you're subtracting. So you're going to have 1 subtract I in this case. So again, don't forget, you got to take I and divide by 100. So it's going to be 1 minus 18, or 0.18. Okay, so our equation is going to look like this. We're starting with 500, 1 minus 0.18, exponent x. Now, it wants, the levels are less than 150. Well, that means that's your Y2. Here's Y1. You're going to put 150 into Y2 and solve for x, because you want the minimum number of filters. So that's x. You're solving for x here. Okay, so you're going to do an intersect, and you will get around 6 filters needed. So a minimum 6 filters. Okay, so you need a minimum of 6 filters. How come? Because you get 6.06685, and it runs on forever, of course. So that's what you would solve for x. So we round that to approximately 6 filters. Taking a look at number 7, we've got a doubling time for bacteria. Our doubling time for bacteria here, our window we're going to use is going to be -5, 15 and 1, -5, 15,000, and we're going to count by 1,000s. Our equation, A equals 50 times 2 exponent x. Now, we can either do it Y1, Y2, put them into Y1. Y2 is going to be 10,000, because you want to find how long. So you're solving for x here. Or we could have put 1,000 equals 50 times 2 to the x and done it by logs and solved it using logs algebraically. We don't have to. We can use our handy-dandy calculator here. So when you do an intersect, you're going to get 7.643, and it's a run-on decimal again. So that means it's about 7.6 minutes, because time is in minutes here. So around 7.6 minutes it takes for the population to reach 10,000. Okay, looking at number 8, a good window for number 8 would be -50, 400, and go up by ones or even 50s is fine. -50, 80, you can count by 10s, that'll help. Okay, the equation would be A equals 480 times a half, because we're talking about half-life, exponent x over 45. Now why is 45 on the bottom? Because it's telling us that the half-life takes 45 minutes. Okay, so every 45 minutes it cuts in half. That's why 45 goes in the bottom. Now, we want to find out how long, so we're solving for the x on top, does it take to go to 15 milligrams. So I'd substitute 15 for A, and you can solve it algebraically with logs, or you can do y1, y2, and do an intersect again. You're noticing we're doing a lot of intersects with our graphs. You need to know how to use your graph and your calculator. So you're going to get a value of x. X is going to be 225. That means 225 minutes. Now, if you want to change that to hours, you would take 225 minutes times 60 minutes per 1 hour. Okay? So what you're actually going to do is, times 1 hour for 60 minutes. That's how we get rid of the minutes. Minutes on top. So what we're going to do here is we are going to take 225 and we're going to divide by 60. So 225 divided by 60, that's going to give me hours. So about 3.75 hours. So about 3 3/4 hours. 3 hours, 45 minutes, that is. Okay, let's look at our next example. Again, it's another population growth one. When you take a look at this, A is asking for the equation. Our equation is going to be, you're going to end up with y equals 8.864 e exponent -12. That's our A value. Okay, that's A, timesing by the B value of 1.0217 exponent x. Okay, so that's A times B there. Because remember, when you put a regression in your calculator, okay, you're actually going to find that it's going to be, so when you're putting you're going to put list 1 is year, list 2 is population. Okay, so when we do that, we're getting that for an A value, that for a B value. Very large numbers. You're going to notice that e to the -12 means it's a very small number. That means I would move my decimal place to the left 12 times there. Okay, so that's my generic equation. B is saying, how long, if it continues this growth rate, in 2011? Well, what year did we start at here? Well, we got our years here on the left, so that means we're going to have to be solving for, or we just substitute, 2011 into x. When we substitute 2011 into x, or we can, since we have it in our calculator, we can actually do solving it graphically. Okay, and again, we can go second trace. We know the value of x equals 2011. So we're going to get our population to be equal to 541769664. So basically around 54 million. Okay, is what they expect the population to be after or in 2011 at that growth rate. Example 10. Here's a common example. The window we're going to use for this is -5, 300, count by tens, -5, 50, count by tens. Okay, it's giving us the equation. So all we've got to do, in A, we're going to put 24 in where the t is. Okay? When we do that, we're going to get an answer of our PT, which stands for y. It means the same thing as y. So PT or y is going to be equal to 69.4 repeating. So what that means, approximately 69 barrels per week. Okay, that's what it's telling us. On B, we're going to sub for PT, okay, so that goes into PT, and we can solve that algebraically, or we can put it into y2 and do it graphingly and solve for x. We want to know what week. We're solving for x, the time value. So when we do that, we're going to notice that x will equal approximately 79. So around week 79, so it's going to take about 79 weeks. Okay? Okay, or sorry, around week 79 is when it's going to be producing 30 barrels per week. On letter C, you're going to put, instead of 50 or 30 into Y2, you're going to put 5 into Y2. When you do that, again, you're solving for X. You're going to get 197.172, and it runs on again. So that's around week 197. Okay? All right. Last example. The window we're going to use here is 0, 15, and 1, 0, 300, and count by 50s. Okay, the equation we're going to get is y equals 69.685 times 1.097 exponent x. That's the equation we're going to get when we do a regression on this. Okay, so you put into list 1, list 2, do an exponential regression. So when does the population exceed 160? So when is it more than? Okay, so we're finding x. We want to solve for x. Solve or find x. When we do that again, 160 is going to go into y2, and we're going to do an intercept. And when we do that, we're going to find x is going to be equal to 8.953, etc. We can round that to approximately 9 days. Okay, check your answers and see how you did.